Hi, my name is Phillip Johnson, and I'll be reporting on the gas turbine/jet engine. So let's get started. So the objective of this experiment was to just get an understanding of how it works, kind of standard with every experiment, and then to calculate these the mass flow, thrust, the amount of fuel burn in each component, the compressor and turbine work, and finally the isotropic efficiency of the compressor, and all in relationship to how fast the spinning RPMs. Here's just a general diagram, I'm sure everyone's seen it, and just to hammer in how the flow works. It comes in through here, and this is the compressor, and basically just compresses the air. And as the compressed air flows through, some of it comes into the combustion chamber, and some of it flows around the outside of it. The reason for this is because once combustion takes place, if it all went in there, it'd be so hot that the turbine blades would melt, which is a real problem with a lot of material science. It's trying to determine a good material to use for the turbine blades, so it can withstand all the high stress and high temperatures. So the air on the outside, it gets just enough cooling so that it doesn't melt the blades. And so you have the turbine here to basically just get some extra energy out of the system. So with it flowing through, you get extra energy to put back in to help give the compressor some help. And then it gets shot out the back of the nozzle. Here's a bunch of thermocouples that basically take all the readings at the different locations, and that's what gives us our data. Just because I'm a sucker for GIFs, and it is a GIF, not a GIF. I eat GIF peanut butter, I watch GIFs on the internet. So this is actually a fan turbine, and or a jet engine, and this part right here is what you see on the front of an airplane, or 747 or something like that. And it's just for efficiency purposes, because all this air over here is moving slower, faster. This is slowest. And everything coming through here is the actual engine. And so yeah, but this is the general airflow, what it looks like. Theory. So this classic TS diagram. You can see that the dotted or the solid line is the ideal cycle, which we obviously do not have. There's losses throughout the whole system. So you follow this dotted line, and as the temperature increases from 1 to 2 in the compressor, the entropy increases. 2 to 3 in the combustion station, temperature is really going to increase, as well as the entropy. Then finally in the turbine, you see the temperature drops and all continuously increases until finally it gets shot out back and the cycle starts over. So the procedure is written on the wall above the turbine, but just in general, you gotta warm it up for 5 minutes, and then there's a throttle that you can adjust it with, and you take the different temperatures and measurements with that, and then you can, after you record it, you can do all the calculations. And here's the data. Everyone can read that, I hope. If not, I'm obviously going to go through and show you the charts and kind of explain it all for y'all. So yeah, here's where we go. And then, well, you can look real quick. I don't know what's going on with this. These are some of my equations. I saw it. Okay, y'all saw it. I'll get it. I use these equations to get the data on them. Here's the results. So, to start things off, here's the mass flow rate, and kind of comprehensive. As the RPM increases, there's more really getting sucked through. Kind of makes sense. The faster it's spinning, the more it sucks in, the higher the mass flow rate. And this is just the general trend of it. It goes up as I'm talking like that. The thrust. Thrust is basically how much you're getting out of the system. It's like the forward force produced by the engine. And again, as the RPMs increase, thrust goes up. And I don't know what happened with this data point here, if it came back down or what, but still that's the general trend of it going up. Here's a little ratio, or the fuel consumption or fuel burn in between the combustion chamber and outside of it in the whatever in the nozzle. So like whatever doesn't get burnt in the combustion chamber gets sucked in, and that's why when we accelerated real quick, you saw the flame come out the back, because it's not all being combusted in the combustion chamber. And so as we'd hoped, though, the majority of it is getting burned up in the combustion chamber. The work, so the more faster it spins, the more work the compressor is going to have to do to get that spinning. And in turn, the more work we're getting put out with the turbine. So the more you work it, the more work gets put back in. Here's the efficiency of the compressor. Again, the faster it spins, the more efficient it is, just because back what we're saying, the work gets put back in. And so in conclusion, yes, efficiency increases as RPM increases. Most of the fuel's burned in the combustion stage, in the combustion chamber. And Bernoulli's is a good approximation to get the pressure difference in the outlet and inlet. And as I promised, I have another GIF of a guy getting sucked into a jet turret. This is just to demonstrate how much suction is being produced by this thing. And he ends up living. This is fine. He gets, huh?
Is that a dummy or a real cat?
I don't know. It's from Ripley's Believe It or Not. It is a man, and he gets, huh?
Oh
yeah, they can just pull him right back out. He sustains only minor injuries.
The clean shave.
But yeah, with a clean shave too.
No, he got chopped up in that thing. He got chopped up.
So yeah, are there any questions?